My name is Jake Pirkkanen, and the title of my talk is Researching the Effects of the Presence and Absence of Ionizing Radiation, Repair, a Biological Investigation Deep Underground. So when we talk about the biological effects of ionizing radiation exposure in terms of risk, there are really four main models that we consider. The first is an epidemiological model, which is based on survivors of the atomic bomb attacks on Hiroshima and Nagasaki, a linear no threshold model, or LNT, which suggests that there is a linear correlation between an increase in radiation dose and an increase in biological risk, a threshold model, which suggests that below a certain radiation dose there is no risk, and a hormetic model, which suggests that below a certain radiation dose there's actually a reduction in risk. However, at the surface of the planet, there is a naturally occurring background radiation which has been ubiquitous throughout the history of biological evolution, and it comes from sources both terrestrial and cosmic. One of the questions that really has never been asked is what happens in the absence of this natural background radiation, and does this natural background radiation play an important role in biological homeostasis? And so in this sub-background environment, we don't know if the effects will be detrimental or positive. So the hypothesis driving the repair project's empirical investigations are that natural background radiation has an essential biological role and helps to maintain genomic stability, and that prolonged exposure to a subnatural background radiation environment will be detrimental to living biological systems. But where can this question be empirically investigated? There's really only one place, and that's deep underground. So the repair project performs its work within the Sudbury Neutrino Laboratory, or SNO Lab, which is a deep underground research laboratory located within the Creighton Nickel Mine in Sudbury, Ontario. It's located 2 kilometers or 6,800 feet underground and is comprised of about 5,000 square meters of laboratory space, the entirety of which is classified as a Class 2000 cleanroom. There's an enormous reduction in cosmic radiation due to the rock overburden, and HEPA filtration of the air within the research facility helps maintain that Class 2000 cleanroom status, and it's the deepest Class 2000 cleanroom laboratory space anywhere in the world. Getting to the repair project's research space is an exciting commute. It starts early in the morning at the SNO Lab research facility, where you get into all of your underground mining personal protective equipment. You then walk from that facility over to the Creighton mine shaft, where all of the SNO Lab researchers and the miners go underground in the cage. This cage goes down 6,800 feet or 2 kilometers, where you exit the cage and then walk roughly 1.5 kilometers down the mine drift before reaching the outside entrance to the SNO Lab facility. You wash all of the mud and dirt off of your boots and enter the dirty side of the cleanroom facility. At this point, you remove your mining personal protective equipment, take a decontamination shower, and emerge on the other side in the Class 2000 cleanroom space of the SNO Lab research facility. Repair is researching the effects of the presence and absence of ionizing radiation and is a deep underground sub-natural background radiation life sciences research project. And we've constructed within the SNO Lab facility deep underground a laboratory space capable of performing biological research to this end. Some of the infrastructure includes a biological safety cabinet for performing work with molecular biology tissue culture model systems, light microscopy, cell counting capabilities, water bath, centrifuge, a tissue culture incubator, and uninterrupted power supplies, or UPS units. Radon is a naturally occurring radioactive gas which comes from the decay of uranium found in rock and soil. However, deep underground, the levels of radon are much higher than would be found at the surface of the planet. So for any subnatural background radiation experiments, we have to make sure that the model systems are free from exposure to this radiological contaminant. We achieved this by engineering and constructing a specialized tissue culture incubator, or STCI. Unique features of the STCI include an airlock purge chamber through which all supplies and materials enter, a glove port so that we can work with our model systems without exposing them to the air found within the SNO Lab, which has higher levels of radon, a lead castle, which serves as both the incubator as well as extra shielding against gamma radiation, a heating element so that all model systems are grown at the proper temperature, a bubbler to help deal with overpressurization of the STCI, RAD7, which is an instrument which allows us to measure radon levels found within the lead castle, power supply, remote temperature monitoring, which allows us to view from the surface the temperature within the lead castle to make sure that things are operating normally, controllers for the carbon dioxide, nitrogen, and oxygen gases which are fed into the lead castle incubator, a humidifier so that the environment within the lead castle is hospitable to our tissue culture models, and backup power system for all of the elements that help power the STCI. The repair project has three experimental environments: an underground standard tissue culture incubator control, the STCI experimental environment, and a surface standard tissue culture incubator control. But as mentioned, radon represents an extreme experimental contaminant for any subnatural background radiation experiments deep underground because it's at much higher levels naturally. On the left, you can see RAD7 radon measurements from within the SCCI, the air found at the surface, and the air found underground. What we found was that the SCCI is extremely efficient at lowering radon levels, not just much lower than what's found within SNOLAB's air naturally, but lower than what's even found at the surface of the planet at a research facility at the Northern Ontario School of Medicine. This means that we actually are achieving truly a subnatural background radiation environment within the SCCI, at least in the terms of radon gas. This is largely achieved by aging all of our gas that are fed into the SCCI underground for at least a month. This allows, based on radon's half-life, to significantly lower the amount of radon present within that instrument. In addition to radon gas, there are multiple components that make up the natural background radiation environment, so it was important to characterize these in each experimental location. This was largely achieved by GEONT4 Monte Carlo simulation-based modeling of each of these experimental locations. So by considering in the model calculated or measured alpha, gamma, neutron, and muon components, as well as the potassium-40 and carbon-14 constituents of tissue culture nutrient media, you can see on the top right that the equivalent dose rates modeled show that the SCCI is able to achieve a much lower level of radiation environment than found in the underground or surface locations. This gives us validation that any experiments performed within the STCI are truly within a subnatural background radiation environment. On the bottom left, you can see tissue culture flasks containing actively growing cells within the lead castle incubator with the door open, just to give you an idea of what it looks like within. And in the bottom middle and right, you can see the higher and lower energy gamma spectrum, just to show that the SCCI, partially due to the lead castle shielding and other components of the instrument itself, are able to reduce the gamma environment within to below natural background radiation levels. The overall goal of the repair project is to investigate the biological effects of the absence of this naturally occurring background radiation in a variety of complex multicellular model systems, including tissue culture model systems, yeast model systems, and C. elegans model systems. These will be grown in a protracted manner deep underground, as well as in the surface and underground control environments, and on a series of experimental time points on the course of months, we will sample and assay for baseline responses as well as radiation challenges. Some of the assay endpoints that we're looking at are gene expression, cellular growth, survival, DNA damage, mutation, and cellular transformation. And the overall goal is to, again, utilize these to try to answer the question of what happens in the absence of natural background radiation in terms of biological risk. For background information on the repair project, we were able to publish several articles in a special edition of the journal Radiation Research a few years ago that focused on the repair project and the deep underground experiments. This included a commentary on the project's goals as well as the construction of the laboratory space and a review of some of the model systems that were utilizing deep underground in the environment. The first few years of establishing the repair project deep underground, we were able to run a pilot project looking at a lake whitefish embryonic development model, and we found some interesting findings that were recently published in a special edition of the journal Frontiers in Earth Science, titled The Biogeochemistry, Biophysics, Radiobiology, and Technical Challenge of Deep Subsurface Research. The repair project currently has 2 postdoctoral fellows being supervised by Drs. Christopher Tomei and Sujintha Tharmalingam from the Northern Ontario School of Medicine. These 3-year postdoctoral fellowships funded by MindTax are titled The Effects of a Subnatural Background Radiation Environment 2 kilometers underground on Biological Systems and the Role of Natural Background Radiation on Neurological Development and Processes. The repair project is excited to be exploring the world of subnatural background radiation research, a truly novel field of biological exploration. Thank you so much for watching my talk, and I truly appreciate your time.